This is the solution to WEX 401. Okay, so we're given two functions. We need to compose them in both orders to check to see if the composition is the identity function in both orders. All right, so then first I'll do f composed with g. So f composed with g without the composition operator is f of g of x. So now I'll write down f's formula, but everywhere I see the argument x, I'll write a slot. So this will be 2 multiplied by slot to exponent 13, and then add 14. So what goes in that slot is g of x. So now I'll write down what g does. So that will be 2 multiplied by, well, g of x does that, so it will be 13 x minus 14 over 2. So that's what g does. And we'll raise that to exponent 13 and then add 14. Okay, so the exponent 13s cancel because radicals, first 13th radical followed by exponent 13 always cancels in that order. So then it will be 2 multiplied by x minus 14 over 2, and then plus 14. So this right here, this step happens because the nth root of x to exponent n is always x. So this is for all n. Of course, that means for all integers greater than or equal to 2. All right, so now the 2's cancel, and we have x minus 14 and then add 14, and then the 14's cancel, which have just x. So in that order, they are compositional inverses, so that's good. Or, you know, not good or bad, but it just is. So now we'll do it in the other order. G composed with f, evaluate at x. G of f of x. So this will be, well, it'll be 13, the 13th root of, so now I just write a slot, minus 14 over 2. So I need to fill in what f of x does now, so 13th root so f does 2 multiplied by x to exponent 13 plus 14 minus 14 and then over 2. All right. So in the numerator, we can drop the parentheses and the 14s will cancel. So that would be cube root of 2 multiplied by x to exponent 13, and then that all over 2. Good, now the 2's cancel. So that would be 13th root of x to exponent 13. So that's just x. The reason why is because this cancellation, this happens, the nth root of x to n. Now it kind of looks like that one, but in fact notice that the radical, for this one, the radical is on the outside, which means it occurs last. So this is x for odd n, and of course n is 13 in this part A. So we can say therefore f and g are compositional inverses. So the answer to that is yes. For this one, notice that this statement is true for odd n, but it is not true for even n. So when the radical is on the outside and it's an even radical, we can't make that simplification. Knowing that, let's put q last, so that the radical is on the outside. Like that one, so that we're considering q composed with p evaluate at x. Without the composition operator, that's q of p of x. Alright, so then that will be square root. And then I put a slot here. Minus 3 is in the radical, and then plus 1 is outside the radical. And then what goes in the slot is p of x. So now filling in what p does, that will be square root of, now p does x minus 1, all that squared. We'll add 3. Okay, so that's what p does. And then there's that subtract 3, the end of the radical, and then add 1. We drop the square parentheses and the 3's cancel. And we have the square root of x minus 1 squared. Now, if you cover that up, it kind of looks like, don't forget this plus 1 here, so plus 1. We're taking something, squaring it, and then computing the square root. And in fact, in that order, the operations do not cancel. So we get, in fact, the absolute value of x minus 1, and then plus 1. The reason why is because, in fact, the nth root of x to n is the absolute value of x for even. N. As a result, the answer is no. So therefore, P and Q are not compositional inverses, because this expression, absolute value of x minus 1 and then plus 1, does not simplify to x.